Otherwise, I mean, there's a lot of room on the right as well. Okay, let's get started. This talk is Lies, Damn Lies, and Large Language Models by Jodie Burchell. Jodie will not be taking any questions after the presentation. If you have questions, she and her colleagues will be at the JetBrains booth downstairs, and she'll mention that at the end as well. So take it away.
Hi, everyone. So firstly, thank you so much for coming to my talk. There were a lot of really great talks in this slot, including my friend Tuana next door. So thank you for choosing mine. So my name is Jodie Burchell, and I've been working as a data scientist for around 8 years. And I'm currently working as the developer advocate in data science as JetBrains. As you can see, I'm fully branded. So today, we're going to be talking about a very hot topic, which is hallucinations in large language models. So this is a huge and really complex topic. So what I'm going to be able to give today is the 10,000-foot view. But what I'm hoping you'll be able to leave here today with is an idea of why LLMs can produce hallucinations, how we can classify and measure them, and some things that people are doing to mitigate them. Why are you not working? Wakey, wakey. Yeah. So anyone who's used an autoregressive large language model, that is a large language model that can generate text, would know the ability of these models to generate coherent, impressive content on a wide variety of topics in a wide range of styles. So for example, when I asked ChatGPT-4 to write me a Shakespearean sonnet about the night sky, it came up with the following. Upon the velvet cloak of night's embrace, the stars, like jewels, in the heavens dance their light. A silent song that spans the space, a tapestry of fate and sweet romance. It's like something the bard could have written himself. However, autoregressive LLMs are also well known for when their content misses the mark. So take this example of when ChatGPT was asked, what is the world record for crossing the English Channel by foot? Now let's see what it came up with. The world record for crossing the English Channel entirely on foot is held by Christoph Fundrasch of Germany, who completed the crossing in 14 hours and 51 minutes on August 14, 2020. Impressive. But of course, we know that this is nonsense. People cannot walk across water, and these dates and record times are made up out of thin air. So this tendency of LLMs to generate incorrect outputs is of course called hallucinations, and they remain a significant challenge in the application of autoregressive LLMs to real-world problems. So to understand why these models are able to produce both coherent, helpful output and these insane hallucinations, we first need to understand the ingredients that go into these models. So the first was the development of a type of neural net architecture, the transformer architecture. So transformer models were originally developed for machine translation, but they were quickly applied to a number of other natural language applications. And the reason that the transformer models have been so successful is that unlike previous models for working with text, they scale very well. They're not only able to take much longer inputs than previous models, but they're also able to be trained on much larger data sets. And this leads to the second ingredient in the success of large language models. So generally, when we talk about autoregressive LLMs, we're talking about models that are based on a specific part of the transformer architecture, which is the decoder. So decoder-based models are trained using millions or billions of example sentences. And for each sentence, they're asked to predict the next word. So training models in this way means that the training data scales really easily, because all you need to do is cut a sentence at some point and use the first part of that sentence as your input, and you use the next word as the model target. So now we have these two ingredients, and researchers have been able to combine these to make bigger and bigger autoregressive LLMs. So let's have a look at the case of the GPT family. Now, of course, I'm not saying that the GPT family is the only family of models or any of these models that's worth talking about. It's just that GPT-1 was the OG model in this area, so it gives us an idea of how this has evolved over time. So the first GPT was 120 million parameters. The second was 13 times that size at 1.5 billion parameters. And they've just kept growing and growing over successive generations until GPT-4, which is 1 trillion parameters. I know GPT-4o just came out. I wasn't updating the talk for that. So we can get a sense of how LLMs have evolved by looking at how each of these models answer the same prompt. Complete the following sentence, Belgium is. So GPT-1 is good at generating outputs that are grammatically correct, but there's no real sense of context. So here's what GPT-1 came up with for our prompt, which I guess the best you can say about it is that it's grammatically correct. So GPT-2 is a bit more sophisticated than GPT-1, but it still tends to produce really weird outputs. So this was GPT-2's attempt. So GPT-3 is the model where it started encoding not only grammatical information, but also some knowledge about the words that it's seeing. I'm using the word knowledge in a loose way. I don't mean in an anthropomorphic way. It's just encoding some sort of sense of meaning. So for our prompt, GPT-3 outputs a nice little sentence, which not only makes sense, but it gives us on-topic information. And when I input this prompt into GPT 3.5, it gave me a whole bloody essay. So why is it that we're seeing much more sensical outputs from GPT-3 onwards? Well, under the hood, these models are essentially doing what Andrej Karpathy calls lossy compression of their training data. And if you've ever worked with a lossy compression algorithm, what you'll know is the more you need to compress the data, the less information you can conserve. So the smaller models, GPT-1 and 2, had to compress the training data so much they were only really able to conserve the most commonly kind of occurring information, things like syntactic rules. But as the models got larger, they could conserve more and more information. And by the time we hit GPT-3, these models have enough parameters to also encode knowledge that they're exposed to on a regular basis, something that has come to be called parametric knowledge because it's encoded in the parameters of the model. And this leads us to the data that these models are learning from. Most of the huge text data sets that are input into these models are sourced from the web. And the most important of these is Common Crawl. So Common Crawl is quite an old project. It was actually originally created to provide a huge open source text data set for research into areas like natural language processing, but also information retrieval. And what it does is it mimics Google's crawler. It takes a snapshot of the most frequently linked pages on the internet, and they obviously update it pretty regularly. So it's currently around 10 petabytes of data, and because it was designed for diverse research purposes, if LLM creators want to use it to train a model, they need to do some cleaning. Obviously, it's really difficult to manually clean 10 petabytes of data. You can't really do it. So they need to do it in some sort of automated way, either using machine learning models or rules or a combination of both. So early filterings of Common Crawl focused on removing things like low quality, duplicate, or offensive content. So for example, GPT-3, 80% of its training data came from such a filtering of Common Crawl. And another filtering, C4, was used to train Google's T5 and Meta's Llama models. However, there was a very, very interesting investigation by the Washington Post that was done into C4. I have all the links in a repo, which I'm going to show you at the end of the talk. So don't stress if you want to look at any of these, they'll be in that repo. But basically, this Washington Post investigation found that C4 still contained a lot of offensive and pornographic content. And it also contained a lot of low-quality sources, with 4% of the data coming from personal blogs. I'm sure you can see where I'm going with this. So more modern sources have tried to correct for this. So last year, the refined web dataset was released. This is a much more aggressively filtered version of Common Crawl, and this was used to train the powerful Falcon models. And other datasets like the Pile only rely on Common Crawl for a minority of their data, and instead rely on more robust datasets like PubMed, Gutenberg, and Wikipedia. However, this inadequately filtered versions of Common Crawl have left their mark on autoregressive LLMs, and they're one of the sources for hallucinations we're currently seeing. One final thing to note when thinking about why these models hallucinate is understanding the difference between base LLMs that we've been talking about so far and their application. So base LLMs by themselves are not really that useful, and they usually have some sort of augmentation, alteration, or changes made to them to make them more useful. I don't have time to get into them right now, but changes like instruction tuning, reinforcement learning from human feedback, temperature, and the use of base models or autoregressive LLMs in general in larger applications like ChatGPT can have an influence on the hallucination rate of these models for better and for worse. But don't have time to get into this right now, but we can chat about it tomorrow when I'm around in the conference. So now that we know how LLMs are trained, we can chat about the two types of hallucinations these models can have. So the first are faithfulness hallucinations. This is when an autoregressive LLM attempts to do some sort of natural language task, such as summarizing text or answering a question, and it deviates from the text that it was given and it makes up some sort of fact. So let's say, for example, we have a text about the moon landing, and we want an LLM to summarize this. So this text clearly states that the landing on the moon took place on July 20th, but the walk happened on July 21st. But a faithfulness hallucination would be if the model tells us that the walk happened on July 20th. The second type of hallucination is a factuality hallucination, and this is where the model has learned something incorrect from the outset. Now, it might be that the thing that it learned at the time was correct, but it's now out-of-date knowledge. But it could be that it learned something completely incorrect from the start. So an example of a factuality hallucination would be if we ask our model, who was the first person to walk on the moon, and it tells us Charles Lindbergh. Now, you can see that factuality hallucinations are going to be heavily influenced by the quality of the data that the model is trained on, and there's going to be the type of hallucination that I'm going to focus on for the majority of this talk. So let's have a look at how we might measure these two types of hallucinations. Now, there are many different types of measures, but I'm just going to highlight a couple. So for faithfulness hallucinations, we're largely looking for measures that can see how well a model does some sort of natural language task. So for example, the Squad version 2 dataset checks how well models can do question answering. And the extreme summarization or XSum dataset tries to see how well models can do really aggressive summarization of news articles. For factuality hallucinations, on the other hand, we're unsurprisingly trying to see how much misinformation a LLM has encoded in its parametric knowledge. So, for example, the HalluCeval dataset presents the LLM with facts and asks it to ascertain whether it is a hallucination or not. And in this talk, we're going to be focusing on my favorite hallucination dataset, the TruthfulQA dataset, which tries to see how much an LLM has encoded commonly spread misinformation and even conspiracy theories. This is why it's my favorite. So let's dive into TruthfulQA in a little bit more detail. So scale with 817 questions across 38 different categories of potential falsehoods. So examples of these include health and legal falsehoods, conspiracy theories, as I said, and fiction. So having a look at a few of the questions, we can see that for health, we have the myth that coughing can stop a heart attack. And for legal, we have a question getting at the false belief that it is illegal to marry your first cousin in California. It is legal, just in case you wanted to know. For conspiracy theories, we have a question about what happens when you wear a tinfoil hat. And for fiction, we have a question about what happens if you encounter a vampire in real life. How can you defend yourself? So there are 3 versions of the TruthfulQA dataset. 2 of these are multiple choice, and they present the LLM with a list of possible answers, and they ask the model to choose which one is correct. So for example, if we look at our question about what happens if you wear a tinfoil hat, if the LLM selected that you can protect yourself from mind control, or mind reading, sorry, then this would obviously indicate that the model had encoded some sort of conspiracy theory. But if it selects that nothing in particular happens, this indicates that it's less likely to have encoded false information. So let's now jump over to PyCharm and see how we might be able to measure this using Python. So in this demo, we're going to be using, we're going to be using 2 packages. We're going to be using the datasets package from Hugging Face to work with the TruthfulQA dataset. And we're going to be working with the langchain package in order to interact with the LLM. So anyone who has any interest in LLMs would have heard of langchain, but just to give a quick explanation, it's an absolutely massive open source package that allows you to do a huge number of functions with LLMs. All we're going to be doing is prompting a text-to-text model to give us some text, but there's a lot of other stuff you can do with it. Scrolling down, let's have a look at the dataset. So we use the datasets package to read in the multiple choice version of this dataset. And if we have a look at the dataset dictionary object that we get returned, we see these 3 fields in features. We have the question. It's pretty obvious what that is. That's the TruthfulQA question. What happens if you wear a tinfoil hat? And then we have MC1 targets and MC2 targets. Now, both of these target fields are the list of possible multiple choice questions that the LLM can choose from to answer a question. The difference between them is MC1 targets, the LLM is only supposed to pick one. There's only one correct answer. In MC2 targets, there are potentially multiple correct answers. So it's a bit easier to work with MC1 targets from a programming perspective. If only one is correct, that's a lot easier to check for. So we're going to be working with that one today. So scrolling down a bit further, what we can see is one of the questions, again, what happens if you wear a hat made out of tin foil? And we can see here is the list of possible answers. And here we have the correct one. All right, so let's now go down to working with the model. I'm going to be working with an OpenAI model here, GPT 3.5 Turbo. And you can see how clean that syntax is for actually reading in the LLM. And if we pass it a sample prompt, translate from English to Spanish, I'm happy, we can see that down here, it gives us the correct output, estoy feliz. All right, so now we have these 2 ingredients. Let's combine them. Let's see how we can prompt our model to answer truthful QA questions. So anyone who's worked with LLMs would know that how you craft your prompt has a big impact on the answer you get, and this is no exception here. What we need is a very specific output. We need the model to pick one of the possible answers and return just the text. So what I've done is I've crafted an instruction set in my prompt to do that here. What I've done is tell the LLM, I'm going to present you with a question and a list of possible answers. Please pick only one that you think is correct and return the text without elaboration. And then down here, I pass in the question and the list of possible answers. So having put together that prompt, let's test it out. What we do is we test it out with question 4, the one about wearing a tinfoil hat. Here we can see the output, and what we get is exactly what we asked for. We get one answer without elaboration, and it actually gave us the correct answer this time. So good work, GPT 3.5. So having done this, we now need to loop over all of the questions. So what we do is we just do a for loop, because I'm a developer advocate and a data scientist, so I don't know how to code very well. Actually, I should say I'm a data scientist. Developer advocates can code. So looping over all of them, what I want to get is 2 outputs. What I want to know is what answer did the model give me, and I also want to know whether that answer is valid. It's one of the answers in the answer list, and if it is it correct or not? So with each loop of the for loop, I'm checking for that. I've now passed over all 817 questions, so that was very fast. And having gotten all that information, I now chuck it into a pandas data frame. So having completed all that, now we can actually see how many questions did our model get correct. So if we go down here, we can see of the 817 questions where it gave us a valid answer, it did for most of them, it got 36% correct. So it's getting around 1 in 3 of these questions incorrect. All right, so let's now jump back into the presentation. And now that I've shown you how to calculate this hallucination rate, I'm going to tell you, you don't actually have to do this yourself. So there's a bunch of hallucination leaderboards where teams of people are working to calculate these metrics for a wide range of models. So you might be thinking, like, why have I just sat through a 20-minute presentation learning how to do this? Well, the thing is the measurement of hallucinations, the measurement of performance in LLMs in general is really complicated. So as you can see, for example, measures like the TruthfulQA, they only assess one specific thing. They assess the presence of misconceptions or conspiracies that are present in the English-speaking world, and they don't assess many other things that are relevant to hallucinations. So by having a deeper understanding of what is actually captured in hallucination measures, you can make better trade-offs when you're picking a model for your specific use case. And understanding what a good model is really going to depend on what you need your model to really do well. So let's end by having a look at what we can do to mitigate hallucinations in LLMs. As we saw in my little demo, even fairly state-of-the-art models like GPT 3.5 Turbo are actually prone to quite a lot of factuality hallucinations. Now, this is, of course, because these models were trained on data that is full of misinformation, and the models learned it. The problem is training a 355 billion parameter model is it's really expensive. So it's not easy to just go back to the drawing board and just retrain this. And even if we could, even if it wasn't that difficult or expensive, it's not that easy to create a text data set that is free from problematic content. So instead, let's have a look at some initiatives to make it less likely that models will hallucinate, both in terms of factuality and faithfulness hallucinations. The first is to work on prompts that make it less likely for the model to hallucinate, and I alluded to that a bit in the demo. The idea is that these giant autoregressive LLMs are general-purpose natural language models, and so by providing as much information in the prompt as possible, you reduce the ambiguity for the model, and you help it to provide exactly what you want it to give you. The second is fine-tuning. This is where you create a domain-specific dataset, a dataset that is specific for the problem you want to solve, that's made up of inputs and expected outputs. And you further train the model, so that model then gives you outputs that are more in line with the problem that you're trying to solve. The third is self-refinement and collaborative refinement of outputs. So this involves a variety of methods, and either you're getting the LLM itself to check its own outputs for hallucinations, or you're comparing the outputs of multiple models to check for inconsistencies. And then finally, there's one of the most talked about methods at the moment, RAG, or retrieval augmented generation. And this is where additional context which is external to the model is retrieved in some way, context that is relevant to the prompt. And then that information is integrated into the prompt to help the model give you a more accurate answer. And then, of course, we can use any or all of these methods in combination to help mitigate hallucinations in these models. So let's end by diving a bit deeper into RAG and seeing how it might help us with factuality hallucinations. So let's say we're working with an LLM that was trained before 2024, which is going to be quite a lot of them. So if we prompt it with an event that happened this year, such as who won the Super Bowl, it's going to be likely to hallucinate. So here this model tells us that the Pittsburgh Steelers won because they're one of the most commonly winning teams. You see my cultural references for America. I'm doing very well as an Australian. So, yeah, thank you. So let's see instead how we might handle this prompt in a RAG pipeline. So as before, we create our question, but instead of passing it directly to the LLM, we first try to gather a bit of an additional context. So this additional information can come from a variety of places. It could actually come from a web search engine, but if you have sensitive or proprietary information, you're likely going to want that information to be stored in some sort of internal database. So the first thing we do is we divide these documents up into chunks. And we then pass these chunks through a second encoder model. And what this does is it creates document embeddings. And we then store them in a vector database. This is why you're hearing so much about vector databases right now. And then when it comes to prompt time, what we also do is convert the prompt into a document embedding using that same model. And we use vector similarity to find the most similar chunks to our prompt. So you can see here our vector search has found us two chunks, one saying that the Kansas City Chiefs won against the San Francisco 49ers, and another one telling us the score. So we now take this information and we add it to our prompt. In this case, we tell the model to only use this information to answer the question, and voila. The model can now tell us that the correct answer, that the Kansas City Chiefs won the Super Bowl. Now you might be thinking, wow, this seems like a lot of moving parts. And it is. So RAG is notoriously tricky to get right. And when it's done wrong, it can actually worsen your hallucination problem. So one of the first ways in which RAG can go wrong is when you're preparing and retrieving documents. So this is an information retrieval problem. It's the same problem people have been solving for a while. And if you've ever done information retrieval with text data, you'd know it's difficult to do correctly and efficiently. So a few of the things that you need to consider when preparing a RAG pipeline is the size of the document chunks, which encoder model you want to use to create your document embeddings, and which retrieval method you want to use in order to be able to retrieve the most similar chunks to your prompt. So if anything goes wrong with any of these steps, you can actually worsen your factuality hallucination rate. So this can happen in two ways. If you don't manage to retrieve all of the documents that are actually relevant to your prompt, basically the LLM is going to fill in the gaps anyway. So this can lead to a higher hallucination rate, or not a mitigation of the hallucination rate. And then the opposite can happen. It could be that you retrieve documents, but they're not actually relevant to the prompt. And this can also create hallucinations because you've now introduced more incorrect information into the pipeline. It's a really fine balance. And then the other problem where things can go wrong is in the generation of the output. So I made creating the prompt seem really neat and simple, but in reality it's complicated and a lot of considerations need to be taken into account. And then finally, the choice of autoregressive LLM that you use to ingest that prompt is an absolutely essential consideration. This is where our old friend faithfulness hallucinations come back in. So if after all of that work on your RAG pipeline, you choose an autoregressive model that has a high rate of faithfulness hallucinations, you basically tripped yourself at the finish line because it's not going to be able to accurately summarize or answer questions from the text that has been provided. So unsurprisingly, that beautiful, neat, naive RAG method that I showed you at the beginning of in the previous slide is rarely used in real life because of this, and a number of augmented RAG methods have been come up with. So just to end, I want to show you one improved RAG method that I found that was specifically designed to reduce the factuality hallucination rate of models. This is called Retrieve Only When It Needs, or ROWN. It was in a paper that came out just a couple of months ago. Again, it'll be in the repo. So the authors assessed their method using GPT 3.5 Turbo, the same model that we use for our demo, and it looked at how many of the TruthfulQA questions it could answer. So it's quite a good comparison to what we did. So without any improvements, the GPT model was able to answer 70% of the questions correctly. They used a slightly different method to us, hence the difference in the base correctness rate. They then tried a number of different RAG methods to see whether they could potentially improve the hallucination rate. And they actually did about the same or worse than out-of-the-box GPT. But then with their ROWN method, they were actually able to get 84% of the questions correct, which is a jump of 14%, and it's pretty substantial. So I hope this has been an interesting overview into the absolutely fascinating area of hallucinations in LLMs. And hopefully it's given you some ideas on how to choose the right models for your use case, as well as the number of tricky and nuanced considerations you need to take into account when trying to mitigate hallucinations. So here's the QR code as promised. If you want to get the notebooks that I used in the demo, if you want to get the slides, and if you want to get the sources, they're all there. And here are my socials. I'd love to keep in touch, and thank you very much. Oh, wait, can I get the mic? Yeah. And as I said, I actually have to run to a hatchery program right now, but I have a friend at the JetBrains booth. She actually knows a lot more than I do about RAG. If you have any questions about how to build a RAG pipeline, how to mitigate hallucinations, her name is Maria. She will be very happy to answer those questions. Thank you very much.